Find the volume of the solid that's bounded by the cylinder, y squared plus z squared is equal to 4, and also x is equal to 2y, x is equal to 0, and z is equal to 0 in the first octant. Let's first try to come up with a picture of this solid region. And let's begin with this cylinder. Because of the fact that the x variable is missing, we know that this can be graphed in the yz plane, and in the yz plane it's a circle with radius 2. So in R3, we have a circle radius 2 in the yz plane that's going to be extending infinitely in the direction of x, or essentially wrapping around that x-axis. However, we're only really focusing on this first octant here, and we've got some other planes that are going to be slicing into this cylinder. The x is equal to 0 plane is the yz plane, so the yz plane is going to serve as like a back wall for our solid. Z is equal to 0 is the xy plane, which basically means that we're only going to be looking at the top half of this cylinder. Since we're focusing in the first octant, we can also get rid of this portion back here. And so far, our region looks like this, kind of like a little piece of quarter round that you might see at the bottom of a baseboard. But there's one other boundary that we haven't taken into consideration, and that's x is equal to 2y. Now x is equal to 2y is itself a plane, and we can determine the graph of that plane by first looking into the xy R2 region and graphing the equation y is equal to 1/2 x. It's a little bit more familiar to look at it from that perspective, which has a y-intercept at 0, 0 and a slope of 1/2. So we'll go up 1, right 2 a couple times to get this line. Now, when we're missing the z variable, that means we essentially graph this line in the xy plane in R3 and then extend infinitely in the direction of the variable that's missing. So let's graph this line in R2 and then extend it infinitely in the direction of z, which is up and down. So when that plane comes up and slices through that cylinder, it splits the solid into two regions. We've got this blue region over here and this red region over here, and the question is, which of these solids are we trying to find the volume of? So let's come back up here to our declarations and see if we can figure it out. The solid that we're after has a boundary that is the cylinder, but the blue region has a ceiling that is the cylinder, and so does this red region. The solid that we're after has to have a boundary that is this vertical plane, but the blue region is bounded by that vertical plane, so is the red region. How about the plane x is equal to 0? X is equal to 0 is the yz plane. The blue region is bounded by the yz plane, but not the red region. The red region has a boundary that is the xz plane, and that would have the equation y is equal to 0. So it looks like we're after the blue region and not the red. So now we get to figure out what that domain region looks like in the xy plane. And let's take a look at a couple of ordered triples. We have the ordered triple 4, 2, 0, which is going to correspond to the ordered pair 4, 2 in the xy plane. Our surface also has the ordered triple 0, 2, 0, which in the xy plane corresponds to 0, 2. And so it looks like our domain region in the floor is going to be this section and not this red section over here. So remember, the volume is going to be calculated by using a double integral. The integrand is going to be the ceiling function, or the surface that's on the top of that solid, and then we'll say dA for now until we decide on our order of integration. But let's consider what that ceiling function would be. The cylinder was y squared plus z squared is equal to 4. And that is the ceiling function, but we need to solve that ceiling function for z to get a function of x and y, and that would be our integrand. So solving this for z, we're going to get plus or minus square root of 4 minus y squared, but because the z values we're looking for are in the first octant, they're going to be positive, so we can ditch the plus minus and say we're only looking for the positive z values. So now let's think about the order of integration. Up here in this region, if we drew a little tiny rectangle, we see that we really do have the option of going with respect to y first. We'd have the same upper and lower limits throughout this region. Or we could integrate with respect to x first. We would have the same lower and upper limits throughout the region there as well. But let's notice, if we integrated with respect to y first, we would have dy here as our inside iteration, and that would take all of this integrand and treat it as a variable quantity. And in order to calculate the integral of that inside iteration, we would need to use trig sub. and that would be pretty time consuming. Since we have the other option to go with respect to x first, let's see if that makes the integration any easier. If we go with respect to x first, all of this is now treated as a constant, and that already sounds like a more appealing way to start. So to get our limits with respect to x, we're going to need to get our line equation back here. This boundary line was the equation x is equal to 2y, or y is equal to 1/2 x. Since we're integrating with respect to x first, we cannot have any x's in this inside iteration, which means that we're going to need this 2y version of the line instead. So with respect to x, the lower limit, or the smallest value of x, is going to be down here at x is equal to 0, and that doesn't change throughout the region. And the highest value of x is going to be on that line, but we want to use the 2y version of the equation of the line. And then we want to take that band and think about it at the extreme low point, which would have a y value of 0. And as well, thinking about that band at the highest location of that interval, and at these high points, the y value is going to be 2. And so that's our upper limit. So we're finally ready to begin the integration, and we'll start with the inside iteration first, which is going to be the integral from 0 to 2y, square root 4 minus y squared dx. And as we mentioned, that 4 minus y squared is a constant multiple, so we can pull that out. And then we'd be looking at the integral of 1 with respect to x, which is just x. Then let's apply the limits of integration, and since we integrated with respect to x, these limits are x limits, which means that we'll be plugging them in for x's, not y's. So the 4 minus y squared under the radical stays put, and the upper limit of 2y gets plugged in for the x, and then subtract 4 minus y squared, and then we plug in the lower limit of 0. So this simplifies down to just being 2y times 4 minus y squared, which then becomes the integrand for the second iteration. So the second iteration goes from 0 to 2. Our integrand is 2y square roots 4 minus y squared, and now we're integrating with respect to y. And thankfully, this can be evaluated using a simple u sub. We're going to let u be equal to 4 minus y squared, so that du is equal to negative 2y dy, and we can create that du by multiplying by negative 1 in here, and then another negative 1 out here to cancel each other out, so that we have negative 2y dy in our integrand. That's just our du. So when we change everything over to u, we end up with negative u to the 1/2 power du. And this antiderivative is going to be 2/3 u to the 3/2. But then we need to go back to y in order to apply our y limits. So that'll be negative 2/3 4 minus y squared to the 3/2. And the y limits are from 0 to 2. Let's pull out that negative 2/3 and plug in the upper limit of 2 minus the lower limit of 0 plugged in, which gives us negative 2/3 times 0 minus 4 to the 3/2, and this all simplifies down to being positive 16/3. Now let's notice that this volume turned out to be a positive number, which should be the case because the solid region whose volume we were after is entirely above the xy plane. And again, the volume of this region was 16/3 units cubed.